Hey everybody. Today we want to talk about the last little section here in chapter 2. This is 2.7, and we're thinking about inequalities. All right. Inequality is when it's not equal to, it could be less than or equal to, or greater than or equal to, or just greater than, or something. So we're going to look at all of that. These are pretty interesting, but nothing really different than what we've already been doing. A couple things to consider, nothing too scary. All right. So first up, I want to tell you about the number line and how to record, how to write down when you see something. Looking at this one right here, you can see that the blue line on that is everything. Where am I? There I am. Which one am I early on now? Is everything from 4 right there all the way up, and that little arrowhead there indicates that this keeps going forever. Okay. So what that little arrow there, the blue arrow, all of that says 4 and everything bigger. So we need a mathematical way to write that and to think about that. If you want to get fancy, we could express it as a set. The set of all numbers that are great that are 4. I'm sorry, the set of all numbers that are greater than or equal to 4. Um, and that's one way that we want to write it. And all numbers greater than equal to 4. And you can see here that we're including 4. See how that one's shaded in right there? Now, there is a notation where they leave that as an open circle, and you wouldn't have the equal to 4. But right now, this one does. So we're 4's in the group, everything bigger than 4. 5.5 is in the group, right? 6 is in the group, 22, 6 million, go as far, go forever, right? So there's two ways that you can write this. The easier way to write it is called the interval notation, interval method. And you very simply start with 4 and you go all the way to infinity. And then you put some little brackets here. Because we're including 4, you would put a hard bracket there. And because you never really get to infinity, we're going to put a soft bracket over here. Okay. Let's do something a little bit different. If I were to draw this right here and go all the way up to 3 and include 3. So here I want to start everything that's greater than 2, and less than or equal to 3. Less than or equal to 3. Okay. So we're thinking about that little piece of space right there. And how do we describe that set of numbers? Well, with the interval notation, it's pretty easy. We're going from 2 up to 3, but here again, the hard bracket and the soft bracket comes into play. We are not including 2, so that he gets a soft bracket, and the 3 over there, we are including that one. So he gets a hard bracket. Okay. We included 4 all the way down to 4. We included 3 all the way up to 3. But we're not including the 2, so that's a softie right there. All right. You can use that, to describe any interval that you come across there. I should say there is one other way to do it, and it's called the set notation. And let's go back to blue here for a second and do that one. This looks kind of cumbersome and weird. but it's something that got cooked up a long time ago when they were trying to describe how these things work. So set notation might say, I need all the values of x such that x is greater than or equal to 4. And we put little not parentheses, what do you call those? Braces around the whole thing. So this would be read as the set of all x, set of all numbers, and then that bar right there is understood to me such that x is greater than or equal to 4. Okay. And you can see how you can get really explicit with that and mark off any set of numbers that you want. Okay. Over here, what we're trying to say is that it's greater than 2 and it's less than or equal to 3. So over here, the set notation might be something like the set of all numbers x such that x is greater than 2 and x is less than or equal to 3. Okay. So there's all kind of ways to kind of get in there and really spell out what you're trying to do. You could also kind of write this as a double inequality if you want. The set of all x such that x is um, greater than 2 and less than or equal to 3. That's probably a little better because it's all in one line now, but see how the X is in the middle? We want these guys in the middle here, and they're trapped between 2 and 3. I'm not including the 2, so I don't have an equal sign. I am including the 3, so I do have an equal sign there. All right. So that's just some different ways to talk about a piece of the number line. All right. Here's a whole bunch more. I don't think we need to worry too much about all these, but you could see the set notation or the interval notation. Here we're talking about everything between two numbers, A and B, and those could be anything, but I'm not including it. They're both soft brackets, so it's an open circle on A, open circle on B, and everything between A and B, all the way up to A, but not A, all the way up to B, but not B. Here, the second one, all real numbers greater than A, but not including A. So I've got my number line, just like before, and here's A, but I'm not including A, so it gets a soft circle there, open circle, and you can see that parenthesis right there that says don't include A, but A 0.000001 counts, right? And it's going to go all the way to infinity. And we never really get to infinity, right? Because there's always more out there. So, uh, that one's a soft bracket too. Okay. What else would be interesting? There's a whole bunch of these here. Uh, I think you can kind of see where this is going. If you got the whole number line, you're going all the way from negative infinity to positive infinity. Of course, you never really get to either end, but everything in the middle, like that. Uh, this one right here and this one are exactly the same thing, except that down at the bottom, we're including A and B, and on the top one, we don't. Okay. So it's kind of fun to play with, whatever. Um, Here are some properties of inequalities, and the rules are made to be explicit for all numbers, but we'll make up some examples here just to kind of think about it. If A is less than B, then A plus C is less than B plus C. I think you can see that that would be true. Here we're adding C to both A and B, and just to pick some numbers, A could be the number 4, B could be the number 7, and right there 4 is definitely less than 7. So I would put it that way. I don't know if this helps or not, but when I was in grade school, I had a teacher and she said, "Oh, all you got to do is think about that sign as an alligator, and the alligator's always trying to eat the bigger number." Okay. So right there, the alligator mouth is toward the 7. That's the bigger one. Let's think about what happens if I take another number. Let's let C be equal to 2. So when I come in here and add 2 to both sides, 4 plus 2 would be 6, 7 plus 2 would be 9, and you can see that the thing is still that way. 6 is less than 9. Okay, that makes perfect sense. So that's the addition property of inequalities, and hopefully that ties that up. Here's another one, the multiplication property of inequalities. And when we think about this one, I'm going to need three numbers again. So A, B, and C. So again, let's let A equal 4, and B can be equal to 7, and C can be equal to 2 again. That's fine. Okay. When I multiply numbers, what we want to show is that AC is less than BC. So here's AC. They're saying that's less than BC. I'm going to put a little question mark, say, is that true up there? A could be 4, C is 2, B is 7, C is 2, and I multiply this out. 4 times 2 is 8, and 7 times 2 is 14. And yes, indeed, 8 is less than 14. So, that one case doesn't prove it for all cases, but looks like we're on the right path there. That makes sense to me. Um, this one, though, the second one says if A is less than B and C is less than 0. Okay, we picked a number that was greater than 0 before, but now we need to say, well, what if that's less than 0? What if it's a negative number here? And let's do the same thing. I got AC and BC. A was 4, C is now negative 2, B was 7, and C is negative 2. And when I multiply this one out, 8 times negative 2 is negative 8, and 7 times negative 2 is negative 14. The bigger one here is the negative 8. Remember, we're on the number line, and here's 0, and somewhere down here is negative 8, and negative 14 is even smaller, right? It's farther to the left. So the 8, negative 8 is the bigger one. I've got to turn the alligator around, and he's going to chomp on negative 8 there. The trick to this is anytime you multiply or divide by a negative number, then you have to flip the inequality sign around. Okay? And that's the easiest way to think about it that I know of right there. But when we're solving these inequalities, you multiply by a negative number or you divide by a negative number, flip the inequality around. I'll show you what I mean right here. Okay, here's an inequality. This is pretty straightforward. If we're trying to solve for x, then it looks exactly like x plus 3 equals 7. We'd know what to do with that all day long, right? We could just subtract 3 from this side, subtract 3 here, plus 3, the minus 3 cancel, and I've got x, and I've got 7 minus 3 is 4. And we still want to keep that as an inequality. If this was in chapter, the rest of the stuff we've done, we just slap an equal sign in there, be done. But this is an inequality. The big question is, did I multiply or divide by a negative number? Well, no. I added, right, or subtracted 3, but I don't flip the sign for addition subtraction. Okay, so this goes the same way. I don't have to change anything. Let's check this one right here. I'm going to come through, subtract 3, that's going to cancel that. Here's a negative 4x, and 7 minus 3. I have not multiplied or divided by a negative number, so I'm going to keep it the same old way. Now I need to get rid of that 4, so I'm going to divide by a negative 4 here, divide by a negative 4 there, and those cancel out. I have x on the left-hand side. I've got 4 divided by negative 4 here. That's going to give me a negative 1. But look at that. I divided by a negative number, and that's when I have to flip the sign around. Okay. Alligator was pointing to the right. Now he's going to the left. You have to remember to flip that around. If I want to graph these things, x is greater than -1. I could come in here. I'm not including -1, but I want everything that's bigger than that. Okay. Just kind of as a little sanity check here. Let's just pick a couple numbers and make sure that we understand why that thing had to turn around. Um, we're saying that 2 should make this statement up here true. So if I come in and go -4 times 2 plus 3 is less than 7. -4 times 2 is -8 plus 3. -8 plus 3 is going to be -5. That is indeed 7. If I hadn't flipped the sign around, it would have been the other way, and that would be a false statement. And I'd be over here on the wrong side somewhere. You could pick one over here. Here's a -2. Okay. So if I take -2 and try it out, and I go -4 times x, x is now -2. I want to add 3. Um, and we're trying to verify that this is not part of the set here. So less than 7. Here's a -4, -2. That would be a +8 plus 3. That's a +11. That's not true, right? 11 is not less than 7. So this should not be in the set of numbers. And the way we flip that sign around, it's not. Okay. If you multiply or divide by a negative number, you got to turn the sign around, turn the alligator around. Here's another one right here. It looks like the same problem, except I don't have that negative in front. Subtract 3, I'd have 4x is less than 4. Divide by 4, x is less than 1. Notice I did not flip it around here, simply because I did not multiply or divide by a negative number. Okay. Right, here's a little bit bigger, more involved one. There's actually 2 here. And what I would do here is to get all, same thing with equations, get all your x's in one pile and all your numbers in another pile, hopefully on the other side. So I'm going to come in here and subtract 10x. That'll get all the x's off of the right-hand side. And I'll have to do it over here to keep this thing balanced. And that will give me a 13 minus 17x is greater than or equal to -4. I added, subtracted there. I don't have to flip the sign. Next, all that 13 is bugging me, so I'm going to subtract 13 from both sides. It's going to look like that. And that's going to give me a -17x is greater than or equal to -17. Again, I did not multiply or divide by anything, much less a negative number. Right here, however, to get rid of that -17, I need to divide by -17. That's going to cancel. Divide by -17. -17 over -17 is a +1. So I got an x. I got a +1. I did divide by -1. So now I've got to flip my sign around to go this way. And I've still got the equals in there. I'm still want to include the equals. So now I've got the hard number 1 there. 1 works, and everything less than that works. So I'd be looking at that arrow right there. Okay. If I wanted to put that in set notation, it goes all the way down to -infinity, or interval notation rather, and I'm going all the way up to 1 and including 1. So I could write it like that. If I want the set notation, I'm saying give me the set of all x such that um, x is less than or equal to 1. You can see that this kind of does the same thing as that right there. So that's not surprising. Over here, got this thing. It's a big mess, but you know what? If you had, just a little simpler problem, if you had, I don't know, 2x equals 4 plus 3x or something, you'd subtract these three x's and get all those x's together, right? This is the same thing. Come in here and get all your x's on one side. I need to subtract 2/3 x in both cases. It's going to cancel on the right. It's going to come over here. I got negative 3/4 x minus 2/3 x. I'm subtracting fractions. So here I got to get a common denominator. That common denominator is going to be 12, right? Between 4 and 3. So here I'm going to have to multiply by 3 top and bottom to get that. And I really shouldn't use the cross multiplication there. Let me put some parentheses. Okay, so I got to multiply top and bottom by 3 here to turn that into a 12, the denominator. Here I've got a 3. I need a 4, so I'm going to put a 4 top and bottom like that, and I'm going to combine these if I don't mess myself up here all in one fell swoop. So what I've got is a negative 3 times 3 would be 9, over 4 times 3 is 12, and that's how many x's I have there. And then down here, this one on the bottom, this guy, I've got negative 2 times 4 would be negative 8. There's the x still sitting there. Downstairs, I got 3 times 4 is 12, like that. Uh, I have not multiplied or divided by a negative number, so I'm going to keep the sign the way it was. And the only thing left after these guys cancel each other out would be the negative 5/8. Okay. I need to combine these two fractions. We already got a common denominator, so that common denominator is 12. Going across the top, I got negative 9x, negative 8x, which would be negative 17x. And I have not multiplied or divided by a negative number. Keep the mark going the same way. I've got this. Here, I need to, what I would do here is simultaneously multiply by 12 to cancel that and divide by negative 17 to cancel this. Another way to say that is to multiply by the inverse on both sides. You could do it either way. Think of it as two different pieces, or, multiply by 12, divide by 17. I don't really care. The only thing left behind is that x, and everything else came over here. Let's see what we got. I got a negative times and divided by negative. So let's let those negatives cancel out. 5 times 12 is 60. 8 times 17. 8 times 10 would be 80. 8 times 7 is another 56. 80 and 56 would be 136. We probably could have found some stuff to reduce right there. For example, 8 is 2 times 4, and this is 3 times 4. So we could have taken a 4 out there, and I'd have a 2 left over and a 4 out of this, and that'd be a 3. And 17 doesn't break down at all. But another way to do that would be to say this will reduce down to 15 34ths. That 2 times is 17. And the negatives all cancel. So either way you want to do it, multiply it big and reduce it, or reduce as you go. Doesn't really matter. However, the point of today's thing is that right there, I did divide by a negative number. And that means I got to turn the alligator around and make him go that way. And 15/34 is a little bit less than half. So that's about here. It's less than or equal. So I am including that point, and I want everything that is less than that. So that would be my thing there. And you can do the set notation, the interval notation, all that stuff. But that's the idea. That's the only difference between solving regular equalities and these inequalities. The only new trick is if you divide or multiply by a negative number, flip the sign around. Okay. Here's a double inequality. And it's possible to do these uh, on both sides at the same time. I find it a whole lot easier just to come in here and break it into two pieces. So I would take this much of it right there and say I've got one condition that says that 3 is less than or equal to 2x plus 2. And at the same time, I want to make sure that this part of it is true right there. So 2x plus 2 is less than 6. Okay. And then just solve those independently. And what this is going to give us is it's going to be some kind of range, either in between 2 points or outside of 2 points. So let's kind of see what happens here. I'm going to come in and subtract 2, just like solving regular equations. Get that x by itself. Let's get rid of the addition subtraction stuff first. And 3 minus 2 would be a 1. That is less than or equal to 2x. Now I need to divide by 2. That's positive, so I don't have to flip anything around. The 2's cancel. I've got my x by itself like I wanted all along. And there's a 1/2 there. So this is fine like it is. I'm going to put a box around it. But very often we're trying to say x is less than or greater than, whatever. So if you want to turn the whole thing around, see how the alligator's going for the x? The x is the bigger one. Just keep that true. Okay. X is going to have to be greater than or equal to 1/2. So 1/2 would be right here. I want to include 1/2, so there's a hard circle. And I'm going to the right. I'm going to just kind of leave it like that right now. I don't know how far I'm going. Maybe I'm going all the way to infinity. Maybe I'm going up to this other value of x. So let's just kind of park it there and see what happens. You're going to do this one the same old way. Subtract 2, and that'll give us 2x is less than 4. And now I need to divide by 2 on both sides, and I'm going to end up with x is less than 4 divided by 2 is 2. Notice I did not divide and multiply by a negative number, so there's my other condition. X needs to be less than 2. Here's 2 right there, and I don't want to include it. This one was not. See how this one's a less than or equal to, but this one's just a less than. So I don't have the equal over here. I did in the first problem, not here. I got a hard bracket on one side, soft on the other, and I want to go from 1/2, including the 1/2, all the way up to 2, but not including 2. Right there. Set notation would be I'm trapped between 1/2 and 2. I do want the 1/2. I do not want the 2. All right. Interval notation. Apologies. The set notation would be the set of all x such that x is between is less than or equal to 1/2. It's just like we wrote it right here. Okay. The 1/2 is less than or equal to x, and then x is also less than 2, like that. So there's the interval, there's the set notation, and down there below we've got the number line. Okay. Absolute value inequalities. We already know with absolute values that there's two possibilities, right? That we're going to have to consider two cases. Consider the positive case and the negative case. All right. So in this one right here, I kind of like breaking it up into two pieces, just like we did before. And I would come in here and say 2x plus 2. This stuff in the middle might have been a positive number, might have been a negative number, but I'm going to separate both of those out. And I would have this, and at the same time, 2x plus 2 um, is less than the negative case. And that's what we did last time with the absolute values. Just break it into two pieces. Maybe that stuff in the middle was positive and I'm trying to get x by itself. Maybe all that stuff in the middle was negative and the absolute values knocked the negative sign off and gave me a positive. Okay, but we're just going to solve it both ways, see what we get. Now, because these are inequalities, the same thing works, right? If I end up, if multiply, divide by a negative, then I have to flip the sign. Okay, flip the alligator. All right. So same old deal. We're going to subtract 2. That's going to give me a 4. I'm going to divide by 2. That's going to be a 2. All right. So that looks fine. Over here, I subtract 2. I'd have 2x. Here it's -6 minus 2 would be a -8. And I divide by a +2, and that's going to be a -4. Did not multiply by or divide by a negative, so that's another perfectly good number there. X is less than 2. Here is 2. I'm not including it, open circle. And um, X is is less than -4. I probably should have flipped a sign here. Here's -4. I don't want to include it. I think we get everything in the middle. There's kind of three pieces of space at this point. We've kind of broken the whole number line. We've got section A here if you want, and section B here if you want, and section C here as divided up. So which ones do we really want? I think I was supposed to flip a sign and put this one over here with a -6 like that. Right, I didn't do that. So, but let's just kind of test it. Let's pick a number, like right here is 0, for example, right? What happens if I put 0 in right here? I'd have the absolute value of 2 times 0 plus 2. And is that really less than 6? 2 times 0 would be 0. There's 2. The absolute value of 2 is 2. 2 is less than 6. So 0 should be on the thing. When I break this into three pieces, if something in there works, everything in there works. So I want all of this. And you're welcome to try any other number in that region that you want. -2 here, for example, I'd have the absolute value of 2 times -2, and we're adding 2. Is that really less than 6? This would be -4 plus 2 would be -2, and I take the absolute value would be +2, and yes, that's 6. So this one's good. All these guys in here are good. Those are going to be the ones that we want. And that's again why I think this sign should have gotten flipped when I put it around over there. So apologies about that. Let's pick a number outside of that real quick and just double check. Here's 4. If I came in and put a 4 up here, I'd have 2 times 4 plus 2. Is that really less than 6? Is that a solution? Is that a number that I want? 2 times 4 would be 8, plus 2 is 10. The absolute value of 10 is 10, and 10 is not less than 6. I don't want 4 in my set, so this one doesn't work, and none of these are going to work in this whole region of space. And see how you can just kind of test any of these that you want. And as soon as you know that your number line's broken into three pieces, you can find the one that you want, even if you forget to do the sign exactly like you should. Okay. We want all those things in the middle. Of course, that is from -4, not including -4, up to -2, not including -2, like that. Okay. Graphical inequalities. Right here, this is kind of another one of these things, but there's going to be one more trick at the end of this thing. What I'm going to do is I'm going to find, I see that it's an absolute value function, right? And I know that absolute value functions make that weird ponk ponk thing like that, where it's almost like a line for half of it and then a line in the opposite slope uh, for the other half of it, right? So I'm going to set all this equal to 0. That'll give me negative 1/2, absolute value 4x minus 5, close absolute value plus 3 equals 0. I'm looking for where y equals 0 because that's the point right there. And I probably shouldn't have colored that in, but you get the idea, right? Um, I'm looking for the roots of this equation, the place where the graph, the function crosses the x-axis. And that's where I'm sorry, where y equals 0. So we did that first, set y equal to 0. Next up, I'm going to solve for x. And I see it's an absolute value, so I know I'm going to have to do this twice and consider both the positive and the negative cases. But no matter what, first thing I'm going to do is subtract 3 from both sides, just like always. And that'll give me negative 1/2, absolute value 4x minus 5 equals negative 3. Okay. And here, next up, I'm going to multiply. I'm going to multiply by negative 2. You could divide by negative 1/2, but I think it's easier to multiply by the inverse. So this 2 will cancel that 2. The negative cancels that negative, and see how I effectively canceled all that together. All I need to do is multiply by negative 2, and that'll take care of that. It's going to leave me 4x minus 5, absolute value 4x minus 5. Negative 3 times negative 2 is a positive 6 right there. Okay. Now's when I pull the absolute value trick, and maybe that stuff in the middle, 4x minus 5, was a positive 6 initially, or maybe the stuff in the absolute value was a negative 6, like so. Okay. Now I've got two linear, well, they're not, they're just solved for x,
I'm
not
not
even.
quite sure how to help you with that.
And thanks, Alexa. Um, 4x. I'm going to add 5 to both sides. That's an 11. I'm going to divide by 4. That's 11 fourths. If it was 12 fourths, it'd be 3. This is 2.75 if you want a decimal version of that. Over here, I would add 5 to both sides, so I'll get 4x. Negative 6 plus 5 is going to be a negative 1, and I divide by a 4, and I get that. Okay? That's those two numbers right there. Right there, I've got negative 1/4, and over here I have 11 fourths right there. So we just found those 2 points. And again, this is kind of going to break my whole number line into two pieces. If you have the graph here, then you remember we were looking for where is y less than 0? Where is it below the x-axis? And if you got the graph, you can just look at it and say, well, y is below the x-axis here, and it's below the x-axis there, and it's not up here. So in this case, I want region A, I don't want region B, and I do want region C over here. Okay, so just let those 2 points that you find break the number line there, and worst case, you could just put some, remember how we did last time? We just drop some numbers in, see what happened. 0 is here in the middle case. So that might be an easy one to check. If I let x equals 0, then I want to drop that into y equals negative 1/2, absolute value of 4 times 0 minus 5 plus 3. And either this is going to come up less than 0, and therefore I want that middle section where 0 is hosted, or it's going to come up positive. I'm going to say, no, that's not the piece. I already know it's not the piece, but let's just see what it looks like when we do that. 4 times 0 is 0. The absolute value of negative 5 is plus 5. I've got negative 1/2 times that plus 5. And then I need to add 3. Negative 1/2 times 5 is going to be negative 2.5, plus 3 is going to equal a positive 0.5. That's a positive number. I want the region where y is less than 0. We just got a positive number, so I don't want anything here in the middle. Okay? I want the stuff that is on the outside like that. Of course, it would be real easy to pick any other number, like -4, -3, -2, or +4, +5, +10, and drop it in there and make sure that when you calculate all this with whatever number you want to drop in for X, that indeed you get a negative number. Okay. So that's that. I guess the last thing to say here about this is notice that they did not include those numbers right there because they would be exactly 3 here. And we didn't have a less than or equal to. We want the ones where they're less than. So it's going to go all the way up to it, but not there. In set notation, let me make a little bit of space here. In set notation, I would have to say that I want to go from negative infinity all the way up to -1/4, but I never get to negative infinity, and I don't want to include -1/4. And also, I want to go from 11/4, but not 11/4 itself, all the way up to positive infinity. And I need to union these two sets. When we union two sets, we're saying take all this stuff and add all that stuff. Okay, so that U right there says put those together, and um, and that would be the interval notation for our answer on that. Okay, well, that's today's discussion about inequalities and absolute value functions and all that groovy stuff. And I hope you enjoyed that. Hope you got lots of questions for Zoom class and for my email box and for my text box, and we'll figure it out. Thanks for stopping by. Have a great day.